Hello everyone, this is Dr. C. I believe this is our last pre-lecture of the semester. Yay! And it might be our shortest. I shouldn't say anything yet, but it's going to be pretty short. And so all we're going to do is, this is actually kind of a review for the final, because we've done this already. All radioactive decay, and we've talked about this as well, follows first order kinetics. Okay, so we're talking about radioactive decay here. So any nuclear decay, and we'll talk more in class about what different types of particles are kicked out of the nucleus, all of it follows first order kinetics. Always first order kinetics. And you might remember these equations. Natural log of the concentration at some time is equal to negative of the rate constant times time plus natural log of the initial concentration. Okay, this is the first order integrated rate law. Okay, and that's all review. We've done this already. There's another version of this that looks like this. Okay, so they're the same equation, just rearranged. I think the first one, so let's call this 1, is easier if you're trying to solve for the concentration at some later time. This one is easy, is easier if you want to solve for K or T. Okay? Now, one other equation you're going to need for kinetics of radioactive decay, first order kinetics, is the half-life. Half-life is very important for radioactive decay. We always talk about the half-life. The half-life of carbon-14 is 5,700 and some odd years or something like that. Okay, so the interesting thing about a first-order half-life is that it doesn't depend on concentration. Each half-life is the same amount of time. So if I had a solution that, say, was 1 molar, okay, and it took, let's say, 10 hours to go from 1 molar to half molar, that would be its half-life, the time it took for the concentration to be cut in half. And so for a first-order reaction, I then know it's going to take another 10 hours to cut the concentration in half again. And then another 10 hours to cut the concentration in half again. Okay, so that's pretty cool for first-order half-lives, that every half-life is the same amount of time. Okay, for other orders, say for a second order, each half-life actually doubles. They get longer. Okay. For first order, they're all the same amount of time, the time it takes to cut the concentration in half. Now, you've worked problems like this before, so I'm not going to spend really any time, but I want to point you in the right direction on one of the take-home quiz problems. Okay? So you have a couple of these in the take-home quiz, and of course there will be a couple in the pre-lecture quiz that you can work. But take a look at problem 15 on the take-home quiz. Now, sometimes what makes the radioactive decay ones a little bit difficult is to express the amount of a radioactive substance. A lot of times we talk about how many counts per amount of time per amount of substance. That seems like a big mouthful. But essentially, this radioactive material is kicking out particles, whether they're alpha particles or beta particles, and we're counting how many of those are coming off. Okay? So we're counting particles. Okay, more particles coming off means higher concentration. Okay, greater amount of that radioactive substance. Fewer particles coming off, lower concentration. So if you see in problem 15, it talks about a sample of a wood from an Egyptian mummy case has a carbon-14 count of 9.4 counts per minute per gram. So that's how many counts are coming off every minute per gram of substance. Okay? Compare that to something that's still living, okay, that would have a decay rate of 15.3 counts per minute per gram. So the higher amount is the initial. The lower amount is the concentration at the later time, right? Once that material, that wood is no longer living, it's no longer uptaking carbon from the the surroundings, okay? And then the carbon-14 will decay over time. So in that now dead substance, the carbon-14 will decrease over time. It'll be lower. So the larger number, 15.3, is the initial amount of carbon-14. The 9.4 is the concentration at that later time. Okay? This one does give you the half-life as well. What can you calculate from the half-life? Bam, the rate constant. Okay, so you'll see that for radioactive substances. You'll have the half-life, solve for the rate constant. You can then, once you have that, plug it back up into one of these equations. Okay? Last thing for this pre-lecture. Look at problem 16. Don't forget we can always talk about percentages. Okay? So the initial would be 100% of whatever it was we start with. We don't have to actually specify the amount. We start with a certain amount of substance. That's 100% of what we got. Now it's going to decay over time. What percent remains? That will be the concentration at the later time. So in that one, you are going to solve for concentration at a later time. Okay? You also you have to use the half-life again to solve for the rate constant, but it's the same substance, carbon-14. Okay? So this one, since you're solving for the concentration at the later time, I would use equation 1. I think it's easier for that. And in 15, what are we solving for? How old? What are we solving for when we say how old? Yeah, we're solving for time. I would use the second equation. Again, you can use either one. It's just it'll matter how much you have to rearrange the darn equation. That's all there is to it. Okay, that's the pre-lecture. I don't know how long it was, but it was pretty darn short. I will see you in class soon. Take care.